Dear students, this is D. Soundarya, Assistant Professor, Department of Mathematics, Sri Bharati Arts and Science College for Women, Kaikurichi. Today we have to study about analytic function. Complex number. A number z equal to a plus ib, where I equal to root minus 1. A and b are any two real numbers is called complex number. Complex variable. A variable z equal to x plus iy, where I equal to root minus 1, x and y are any two real numbers is called complex number. Then complex conjugate. Conjugate of z equal to x plus iy, z bar equal to x minus iy. Modulus or absolute value of a complex is given by the modulus of a complex number z equal to x plus iy is given by modulus z equal to root x squared plus y squared. Then argument or completude. Argument of z is the angle theta between the positive real axis and the line joining the point to the origin. Polar form of complex number variable. The polar form of a complex variable z equal to x plus iy is given by z equal to r cos theta plus ir sin theta, where x equal to r cos theta, y equal to r sin theta. Theta is the angle between the positive real axis and the line joining the point to the origin, and r is the distance of the point from the origin. Euler's formula. E power I theta equal to cos theta plus I sin theta. Modulus and amplitude is given by modulus mod z equal to root x squared plus y squared equal to root of r squared into cos squared theta plus sin squared theta, which is equal to r. Amplitude y by x equal to r sin theta divided by r cos theta, which is equal to tan theta, implies theta equal to tan inverse y by x. Argand plane. The plane which is convenient way to represent any imaginary number graphically is known as the Argand plane. Let z equal to x plus iy, then real of z equal to x and imaginary of z equal to y. Notice r c s theta equal to r of cos theta plus I sin theta. 1 into r squared equal to mod z squared, which is equal to x squared plus y squared, is given by x plus iy into x minus iy, which is equal to z bar. And second one is modulus z1 plus z2 less than or equal to modulus z1 plus modulus z2. The third one is modulus z1 minus z2 greater than or equal to modulus z1 plus minus modulus z2. Fourth condition, modulus z1 z2 equal to mod z1 modulus z2. Fifth condition, modulus z1 by z2 equal to modulus z1 by modulus z2. Sixth one is given by z1 plus or minus z2 equal to z1 bar plus or minus z2 bar. Seventh one is given by z1 z2 whole bar equal to z1 bar z2 bar. Eighth condition is z power n bar equal to z bar power n. Ninth one, z inverse equal to z bar divided by modulus z squared, z not equal to 0. Then we have to see function of complex variable. If for each value of the complex variable z equal to x plus iy in a region R defined on complex plane, there exist corresponding one or more values of w equal to f of z, which is given by u of x comma y plus v of x comma y. Then w equal to f of z is called the function of the complex variable z. Analytic function, that is regular function or holomorphic function. A single valued function f of z is said to be analytic in a region R of complex plane if f of z has derivative at each point of R. For example, any polynomial function is analytic, that is real or complex. The exponential function is analytic, the trigonometric functions are analytic, also the logarithmic functions are analytic. Necessary and sufficient condition for a complex function f of z equal to u of x comma y plus iv of x comma y is analytic. First condition, f of z is continuous defined on the given region in complex plane. Second one, ux, uy, vx and vy are exist. Third one satisfies the Cauchy-Riemann equation, that is CR equation given by ux equal to vy and uy equal to minus vx. Note, the operator del squared equal to dou squared by dou x squared plus dou squared by dou y squared is called a Laplace operator. And the second one, the equation del squared f equal to dou squared f by dou x squared plus dou squared f by dou y squared is equal to 0 is called Laplace equation. Then harmonic equation function, potential function, a real valued function with two variables x and y which is continuous and possesses second order partial derivatives such that satisfies Laplace equation is called harmonic function. Harmonic conjugate is if u of x comma y and v of x comma y are harmonic and w equal to f of z equal to u of x comma y plus I into v of x comma y is analytic. then u is called harmonic conjugate of u and v is a harmonic conjugate of u. Note, first condition, u is harmonic if del square u equal to uxx plus uyy equal to 0. V is harmonic if del square v equal to vxx plus vyy equal to 0. Then second one, u is harmonic, then u can be a real part of analytic function. Construction of analytic function, Milne-Thomson method. The cases are if the real part u of the analytic function f of z is known, three steps are followed. First condition step, find ux and uy, and second one find ux and uy at z comma 0, and third one f of z equal to integral ux dz minus I integral uy dz. Case 2, the imaginary part v of the analytic function f of z is known, three steps are followed. First one find vx and vy, find vx and vy at z comma 0, and third one f of z equal to integral vy dz plus I integral vx dz. Note, suppose to find the analytic function whose combined value of u and v is given, that is the values like 3u plus 2v, u minus v, u plus v, etc. 5 steps are followed. First one, find partial differentiation of given combined value with respect to x. Then find partial differentiation of given combined value with respect to y. Using CR equation, ux equal to vy and uy equal to minus vx, and then convert uy and vy by vx and ux in the equation. Step 4 is solve for ux and vx. Then step 5, we know that f dash of z equal to ux plus ivx, and find f dash of z equal to ux plus ivx at z comma 0 and integrate. We will get f of z. Then exact differential method is follows. Case 1, if the real part u of the analytic function f of z is known, three steps are followed. First one, find ux and uy. Step 2, since f of z is analytic, ux equal to vy and uy equal to minus vx, and by exact differential method, dv equal to vx dx plus vy dy equal to minus uy dx plus ux dy. Step 3, v equal to integral dv equal to minus integral uy dx plus integral ux dy, which is equal to integral uy dx plus integral terms of ux not containing x dy. Case 2, if the imaginary part v of the analytic function f of z is known, three steps are followed. Find vx and vy. Second one, since f of z is analytic, ux equal to vy and uy equal to minus vx, and by exact differential method, du equal to ux dx plus uy dy equal to uy dx minus vx dy. Step 3 is given by u equal to integral du, which is equal to integral vy dx minus integral vx dy equal to integral vy dx plus integral terms of vx containing x dy. Shortcut method is given by case 1. If the real part u of the analytic function f of z is known, then f of z equal to 2u into z by 2 comma z by 2i minus u of 0 comma 0 plus I into c, where c is a constant term. Case 2 is given by if the imaginary part v of the analytic function f of z is known, then f of z equal to 2iv z by 2 comma z by 2i minus iv 0 comma 0 plus c, where c is a constant. Then mapping. Mapping is a mathematical technique used to convert one mathematical problem and its solution into another. It involves the study of complex variables. Let a complex variable function z equal to x plus iy defined in z plane have to convert in another complex variable function f of z equal to w equal to u plus iv defined in w plane. This process is called as mapping. Then conformal mapping. Conformal mapping is a mathematical technique used to convert one mathematical problem and its solution into another, preserving both angles and shape of infinitesimal small figures but not necessarily their size. The process of mapping in which a complex variable function z equal to x plus iy defined in z plane mapped to another complex variable function f of z equal to w equal to u plus iv defined in w plane, preserving the angles between the curves both in magnitude and sense is called as conformal mapping. The necessary condition for conformal mapping is given by if w equal to f of z represents a conformal mapping of a domain D in the z plane into a domain D of the w plane, then f of z is an analytic function in domain D. A mapping w equal to f of z is said to be conformal mapping at z equal to z naught if f dash of z naught not equal to 0, that is dw by dz not equal to 0 at z equal to z naught. Critical point is given by the point at which the mapping is not conformal is called critical point. That is, if f dash of z naught equal to 0 at z equal to z naught, it is said to be critical point. That is dw by dz at z equal to z naught equal to 0. Then z naught is the critical point of the transformation w equal to f of z. The transformation w equal to f of z is conformal at a point z equal to z naught. Then the inverse transformation z equal to f inverse of w is conformal at the same point z equal to z naught. So the critical points of the transformation w equal to f of z is given by dw by dz equal to 0 and ddz by dw equal to 0. Isogonal, the process of mapping in which a complex variable function z equal to x plus iy defined in z plane mapped to another complex variable function f of z equal to w equal to u plus iv defined in w plane preserving the angles between curves in magnitude but not in sense is called as isogonal mapping. Bilinear transformation, it is known as Mobius transformation, linear fractional transformation. Consider ax plus b by cz plus d, where ad minus bc not equal to 0, z equal to x plus iy is a complex variable in z plane, and w equal to u plus iv is a complex variable in the w plane. Also, a, b, c, d are complex numbers, and c and d cannot put 0 simultaneously. This transformation is called bilinear transformation. Note, first condition. The necessary condition for bilinear transformation is given by AD minus BC not equal to 0. Second one, the inverse transformation Z equal to dW minus B by A minus WC is also bilinear. Third one, AD minus BC is called the determinant of the bilinear transformation W equal to AZ plus B by CZ plus D. If AD minus BC equal to 1, then the transformation is said to be normalized. Fourth one is bilinear transformation is 1, 1 and on 2, that is bijective. Fifth one is every bilinear transformation maps circle or straight line onto a circle or straight line. We have to see fixed point or invariant point. The fixed point of the transformation w equal to ax plus b by cz plus d is obtained from solving z equal to az plus b by cz plus d or cz squared plus d minus a into z minus b equal to 0. Cross ratio. The cross ratio of 4 points z1, z2, z3, z4 is given by z1 minus z2 into z3 minus z4 by z2 minus z3 into z4 minus z1. So note, first one, bilinear transformation preserves cross ratio. Second one, if z1, z2, z3, z4 are points in z plane and w1, w2, w3, w4 are their corresponding images on w plane, under a bilinear transformation their cross ratios are equal. That is z1, z2, z3, z4 equal to w1, w2, w3, w4. The second one is when 3 points z1, z2, z3 of z plane and their corresponding images w1, w2, w3 or w plane are given, then the associated bilinear transformation can be found by using z1 minus z1, z2 minus z3, z1 minus z2 into z3 minus z equal to w minus w1 into w2 minus w3 by w1 minus w2 into w3 minus w. Thank you, students.